This is the second lecture for Chapter 2, Atoms, Molecules, and Ions, and this one will focus in on the molecules and ions. So molecules and molecular compounds. First thing when we're talking about combining atoms together is we need a way of representing them, and we do that using a chemical formula. So chemical formula is just a representation of a chemical using atomic symbols and subscripts denoting the number of atoms. So our atomic symbols would be our letter symbols for the atoms from the periodic table, and subscripts are just the numbers written small to the right of the element to show how many of that atom we are using. Well, our first type of formula comes from diatomic molecules. So diatomic means that it's two atoms, so di meaning two, atomic meaning atoms. So it's a molecule made up of two atoms of the same element. Naturally occurring in our world are 7 of these elements. So anytime we find these in nature, so hydrogen, for example, we breathe in hydrogen, we breathe in oxygen, nitrogen. These all come in the form of a diatomic molecule. We don't just breathe in a single oxygen atom, we breathe in an O2 molecule. So these 7, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, are 7 diatomic elements naturally occurring in our world. You do need to know these. And my little way of memorizing them is I call them the Hofbrinkel elements. Just a word made up using the order of these elements as written. So if that helps you, awesome. There is another way using the periodic table I can show you. Just ask me in class, and I'll let you know how that looks. So if it's not a diatomic molecule, but it's still made up of more than, or sorry, let me start over. We have, on top of diatomic molecules, we have molecular compounds. So the diatomic ones are made of the same element. When we have molecules containing more than one type of atom or element, then we can create molecular compounds. So anytime you hear the word compound, it means more than one atom or type of atom, more than one element. And the word molecular is what we need to remember when we're hearing the word molecular or molecule. It's something that is covalently bonded, meaning that the atoms share their electrons. They're going to be made up of non-metals, so that right side of our periodic table, including hydrogen. So molecular compounds are made of non-metals, and they're combined together in covalent bonding. Examples, something like water, H2O. We have their chemical symbols, hydrogen and oxygen. This 2 tells us there are 2 hydrogens. There's no number after the oxygen because we assume if there's no number, there's just one of them. You do not have to write the 1. Actually, don't write the 1. It's not good form. We have carbon dioxide showing us 1 carbon and 2 oxygens. And then we have methane, CH4. We're going to talk about the naming of these later on in this. When we're dealing with molecular formulas, a molecular formula indicates the actual number of atoms in a molecule. So if you look at the molecular formula, it will tell you exactly what the chemical is made of. But we also have something called an empirical formula. This is another type of formula, and it just gives the relative number of atoms of each type in a molecule. It's kind of just showing the ratio of each atom to each other. So an example, our molecular formula for ethane is C2H6. So 2 carbons, 6 hydrogens makes our molecule. That's all that's involved there. But we can take that and reduce those numbers down and just kind of get the ratio of carbons to hydrogens. So our empirical formula would be CH3, 1 carbon for every 3 hydrogens. So that's just kind of our ratio. It's an empirical formula. So when a molecular formula is known, when we know this first formula, we know C2H6, we can always get the empirical formula. We can always reduce numbers. That's not a hard thing to do. But if we're given the empirical formula, we can't always go back to the molecular formula easily, because we don't know that we have to multiply by 2 to get to this. You can't just predict that. You need more information. We'll be dealing with that process later on in another chapter. Now, we have a lot of ways of looking at molecules, of representing them. The molecular formula is an easy way to show the composition or what something is made of. Another easy way is the structural formula, but the structural formula has more to it. It's a lovely way of showing us how the atoms are bonded. So the molecular formula of water, H2O, just tells us 2 hydrogens and an oxygen. But it doesn't tell us that the oxygen atom is in the center and that the hydrogens are each bonded to that oxygen. If we looked at something like hydrogen peroxide, again, we wouldn't know from the molecular formula that it's set up in this structure. And then methane, CH4, we can see the carbon with its 4 hydrogens bonded to it. So our structure formula gives us more information than the molecular formula. Something to take notice of here is that our hydrogen atoms are all only single bonded to another atom. So what that means is that each hydrogen only has one line coming off of it, and those lines represent a pair of electrons. So this hydrogen is sharing a single pair of electrons with this oxygen. Same thing for this hydrogen. So this oxygen has 2 single bonds to it, but each hydrogen only has 1. Again, each of these oxygens have 2 single bonds, but each hydrogen only has 1. Our carbon over here has 4 single bonds. Each hydrogen only has 1. Hydrogen will only ever have 1 single bond, so you can't stick it in the middle of the molecule. It's always around the outside, and only has that 1 bond to it. We have some other representations besides the molecular and the structural formula. Another one is what we call a perspective drawing, where it tries to show us on a flat surface what this might look like in 3D without having something three-dimensional. So anytime something's connected with a solid single line, that's there to represent something lining up with the plane of the page. So our carbons and hydrogens on this side are all in the same plane, so in 3-dimensional space. Now, the way to represent something in a more 3D aspect is they use these wedges. The dotted or dashed one shows something that's supposed to be behind the page, or the plane of the page, and our solid one shows something that's coming out of the front of the page. So this kind of gives us that 3-dimensional effect without actually having something 3-dimensional. It's just a perspective drawing. We won't really draw these a lot at all, but it's good to know what they're representing. Then we have our ball and stick model. This is kind of the next step. It's taking that perspective drawing and actually bringing it out into a 3D image. So it's showing our spheres here for each of our atoms, and these sticks are just representing the bonds and how they're sharing their electrons. Okay? This is what it looks like when we use our molecule kits to create our molecules. Our last one is called the space filling model, and what it shows is the overlap of the electron clouds of each atom. So instead of just showing the kind of the more nucleus or the smaller version of the atom, it's showing where maybe the nucleus is in the center here, but then it shows where the electrons actually can lie and fly around in, so it gives those electron clouds, and it shows that overlap. So our carbon's in the middle there, and it shows the overlap with the electron clouds of each of the hydrogens. So it kind of gives you a better idea of how these things are overlapping with each other and sharing those electrons between them. So we will see each of these. They all have a strong point and a weak point, so it just depends on what we're trying to represent with them. You'll see different versions and different types of structures in your textbook, so it's good to be familiar with them. Alright, our next topic, so that's all molecular compound stuff, so our nonmetals. When we get into ionic compounds and ions, we're dealing with metals and nonmetals, so it kind of brings up more parts of our periodic table. When we talk about ions, those are just atoms with a charge, and a charge can be positive or negative. If it is a positively charged atom, particle, then we call it a cation. Yes, it is pronounced cation. So a positively charged particle which lost electrons to become positive. If we think of a neutral atom, say it has 3 protons and 3 electrons, that's neutral, 3 of each. Well, if it loses some of those electrons, then it has more positive parts, so it's positively charged. So we get cations that way. If you have an anion, it's a negatively charged particle which gained electrons. So if you are neutral and want to become more negative, you have to gain more electrons, more negative particles. Now, when we're talking about these things, we can only lose or gain electrons, negative stuff. So try not to get that confused with, you can't add protons or anything like that. We can only gain or lose electrons. Alright, one other part to these, cation and anion. The way I like to remember the difference between the two words is cation has that T in it, and the T is kind of like a plus sign, so those are positive ones. And anion, I've heard students say they think of onions and they don't like them, so it's negative, or I think anti, so anion is anti, it's negative. A couple ways to remember them. We do need to keep those straight. Alright, if we're looking at our periodic table, we want to easily be able to identify our positive particles from our negative particles, cations and anions, based on where they are on the periodic table. So we will be ignoring for now these transition metals in the middle. We're going to look only at what we call our representative elements. So that's groups 1 and 2A, and then 3 through 8A, the A group. Elements in groups 1 through 3 will easily lose valence electrons. Remember, things want to be like the noble gases in group 8 and have that full valence electron shell. So our elements in group 1, 2, and 3 will easily lose those extra valence electrons and go down to the next energy level where they have that full 8 electrons. So things in groups 1, 2, and 3 will get a positive 1, positive 2, or positive 3 charge when they become ions. Groups 5 through 7 will gain electrons. So when we're looking at 5 through 7, they are going to gain 3 electrons, 2 electrons, or 1 electron to become negative anions. Our group 4 in the middle there, it can kind of go either way depending on the situation. Mostly for us, this is where carbon is actually on the periodic table, and carbon really deals in molecular compounds, not ionic compounds. So we won't see a lot of that plus or minus 4, but it can kind of go either way. So reference. What I want you to do right now is take out your periodic table that I gave you in class, pause this video, and label your charges so you don't have to keep trying to figure out what they are. Label your plus 1, plus 2, plus 3 on the top so you know what your charges are for this. Do that now. Alright, so you should have your stuff all labeled. Alright, so ionic compounds are made when we take a cation and anion and combine them together and form a new substance. We do have to have both a positive cation and an anion, the negative part, to make this. And when we think about this type of compound, it's more of an attraction between that positive and negative than it is a bond like covalent bonding is. Covalent bonding is when we share those electrons, and ionic compounds are when they are attracted to each other like magnets. When we form these compounds, it can be from monatomic or polyatomic ions. You hopefully remember polyatomic from last year. Something that is a polyatomic ion would be something like NO3 minus here. So we have nitrogen and 3 oxygens. They're already bonded together. That's a covalent bond between them. And overall, it has an extra electron that it's gained. So it's polyatomic, more than one atom, and it has a charge. So that creates an ion. So a few few examples of ionic compounds. These all of these examples have one positive charge and one negative charge on the cation and anion. So it makes it very easy to have these things balanced and attract to each other. So we have sodium from group 1A and chlorine from group 7A. With that one positive and one negative charge, they can come together, form sodium chloride and ACl. So that positive and negative cancel each other out and attract to each other, and we get a neutral compound. When we write the compound, these two things together, we don't show the charges because once they're attracted to each other, those charges cancel out, and we don't want to see them anymore. That's what shows us that it's neutral. Same thing here with using a polyatomic ion. We have that sodium again with that positive charge, but this polyatomic ion with a negative charge. That single positive and single negative charge still cancel each other out, and we just write these things together. Okay. We can do this with two polyatomic ions as well. We have a polyatomic ion, cation, NH4+, and we have our negative polyatomic ion, NO3-. Again, that single positive and single negative charge, they can cancel out, and we just write the whole thing together, creating our compound. We'll talk about the names of these later on. So each of these have that balanced positive and negative charge on the ions, so only one of each atom or each ion is necessary to form the compound. But when it's unbalanced, we use what I call the crisscross method to balance the charge and write the symbol for the compound. The way this works is that we're going to crisscross the amount of charge from each atom or each ion to the subscript and create the compound. So sodium has a +1 charge, or 1 plus charge. So we're going to take that 1 and it's going to become the subscript for our sulfur. And our sulfur has a charge of 2 minus, and that 2 is going to become the subscript for sodium. So let's see how this works. The 2 becomes the subscript for sodium, and the 1 becomes the subscript for sulfur. And if we take that and write the chemical formula from it, we don't want to see those charges, like I said, because we're creating that neutral compound. So we write Na2S. So this 2 came from the charge on sulfur, and that 1 is really the subscript on sulfur, but we don't write the 1s. It's one of the conventions in chemistry that we just do not write the 1s. Okay, so that's the crisscross method. So a second example of ionic bonding is shown on this slide. We have magnesium with a 2+ charge and nitrogen with a 3- charge, and we want to make a compound out of this. So again, we're going to use the crisscross method. We take the numbers and we cross them. So the 2 becomes the subscript on the nitrogen, and the 3 becomes the subscript on the magnesium. And when we write it, we get Mg3N2. Again, dropping those charges, this creates our neutral compound. So we have 3 magnesiums, each with a 2+ charge. So 3 times 2 is 6 positive. And then we have 2 nitrogens, each with a 3 negative charge. So 3 times 2 again, we get -6. So we have a -6 charge and a +6 charge, and that cancels out to make a neutral molecule or neutral compound. And then one more example is, again, with the sodium chloride that we're familiar with, is this shows how we're creating our ions. So we start with our sodium atom, and again, those lose their electrons to become positive. So we have those 11 protons in the nucleus, and now we only have 10 electrons in the electron cloud. So when we lose that electron, it becomes positive. That electron gets taken by chlorine. Chlorine gains that extra electron, so now it's 1 more than its protons, and it becomes negative. So now they have this negative and positive ions, and they can become attracted to each other. So we get our chlorine attracted to a sodium. Now when we zoom in on this, unlike something like a water molecule or carbon dioxide that we looked at before, and we saw those bonds with the lines, these are all just attracted to each other. We get what's called a crystal lattice structure, where we have the positive sodiums all interspersed between negative chlorine atoms, and it creates this crystal structure. Now, there's some different shapes to these structures, as in how many atoms are around each other, how many positives are around a negative, but we don't have to go that deep into structures in this class for crystals, but we do need to see that ionic compounds do come in crystals. It doesn't matter if it's this magnesium nitride or if it's something like sodium chloride, they're all going to come in a crystal like this. So any type of ionic compound is a salt. It's a type of salt. So that is our other examples of ionic bonding. Now, when we're dealing with the names, all of these ionic compounds we call inorganic compounds. So ionic compounds are named for their cation and their anion. First thing we do is give the cation its name. So the first element, the first substance that comes up is the cation. We just name it. Nothing changes. Then the name for the anion, then we name the anion by changing its ending to IDE or IDE. So let's look at how that works. NaCl, the cation is sodium, so we could split this in half. We have the cation being sodium, the anion being chlorine, and the anion, we change its ending to ide, so this would be chloride instead of chlorine. So the name of this is sodium chloride. Another example, NH4Br. If we split this into our cation and our anion, we get NH4, which we call ammonium. And we get our Br, which is bromine. We change its name ending to ide, so we get ammonium bromide. And then our last one, we got Ca and Ca2NO3. So we cut this in half to our cation and anion. The cation is calcium and the anion is nitrate. The name for this is actually just calcium nitrate, and the reason we don't change the ending on nitrate is because that anion is a polyatomic ion and it already has its name set. It's done for us. So polyatomic ions have fancy names and we just use those fancy names. Just like this ammonium up here, we called it ammonium. We didn't call it nitrogen hydrogen 4 or something weird like that. So when we're dealing with polyatomic, we're going to look up their names or know them. All right. Now we do have other things that come up when we're naming ionic compounds. We have transition metals, that center part of the periodic table that we ignored. So if a metal can form cations with different charges, then the positive charge is indicated by a Roman numeral in parentheses following the name of the metal. For instance, iron can form a +2 charge or it can form a +3 charge because it can either lose 2 or 3 electrons. So to show which one it is, we use Roman numerals after the name to tell us which form it's in. So iron 2 or iron 3. These will always be for positive charges. Similar for copper. Copper is going to be a +1 or a +2 charge. So copper 1 or copper 2. When paired with an anion, the name must contain the Roman numeral to indicate the charge of our cation. So if I was to make a compound with one of these, say I put iron 2 with chlorine, it would be called iron 2 chloride. That's how we would read it. Alright, another thing we have to name for our ionic compounds are acids that are formed from ionic compounds. So acids are a special hydrogen-containing molecule that we will see often in this class. The hydrogen is written on the front of the acid's formula to help denote that it is an acid. The name of the acid is derived from the anion. So our anion, our negative part, is going to tell us how to name these things. So acids with anions whose names end in ide are named by changing the "ide" to "ic" and adding the prefix hydro to the name. So, for instance, if we have an acid, which is HCl, its anion is chlorine, which we call chloride. So we would call this hydrochloric acid. The "ide" changed to "ic", and we add hydro as a prefix. Another example, H2S. Sulfur is our anion. The name for that is sulfide. So we change it to hydrosulfuric acid. Okay. The other type of acids, acids with anions whose names end in "ate" or "ite, are named by changing the "ate" to "ic" and "ite" to "us." I know that sounds crazy, but it's just some general rules. So the perchlorate ion, we would call it perchloric acid. Chlorate ion, we would call it chloric acid. Chlorite ion, we would call chlorous acid. And the hypochlorite ion, we would call hypochlorous acid. So the "ites" turn to "us, "ates" turn to "ic." We're going to have a few acids that we will memorize in this class, the formulas and names of. This is just to kind of show you where those names actually come from. They're not just randomly chosen. There is a system to all of this. There is a committee, it's the International Union of Physical and Applied Chemists. They decide all this stuff, how to name everything and all the rules. So IUPAC is the group that figures all this out. So there is patterns to it. All right. And last but not least, the names and formulas of binary. Binary meaning two atoms. Molecular compounds. So this is going back to our molecular compounds, our covalent substances. And this is only when there's two atoms there. So binary is a two-element molecule, or two-element, not two atoms. Molecular compounds composed of two nonmetals that are covalently bonded and they have a different naming system. So the way we do this is we name the first element and the second element, changing the ending of the second element to "ide." So it follows the same pattern as our other one to start off with. And then we use prefixes in front of each of those words to denote the number of atoms of each element used in the compound. There's only one exception. We do not use mono for the first element in the compound. So let's look at how this works. Cl2O. So chlorine, we would name that, and oxygen we change to oxide. So there's a chlorine oxide. Then we put the prefixes on it. 2 is di, so we'd say dichlorine. And 1, oxygen, we'd say monoxide or monoxide. This one, we have nitrogen and oxygen, so it'd be nitrogen and oxide. We've got 2 nitrogens, so that would make it dinitrogen. We have 4 oxygens, so it would be a tetroxide. This 4 is tetra. Here's where our exception comes in. N is nitrogen, and F is fluoride. There's 1 nitrogen, but it's the first one, so we don't use mono. We just say nitrogen. And then 3 fluorines, so it's trifluoride. And this last one, tetraphosphorus decasulfide. So these ones are special because they tell us exactly how to write the formula from the name, because there's no charges here to crisscross, so we can't really predict what the formula would be unless we have those prefixes there. So that's a really important part of this. Alright, moving on. The last part of this, I believe, is some simple organic compounds. So at the very beginning, we saw a substance called methane, CH4, this one here. And this is an organic substance. So the study of carbon is called organic chemistry. You will not study organic chemistry specifically in this class, but it helps to know a few of the fundamentals just to help in things like combustion reactions and to recognize some of these names when they're used in the textbook. So the first and simplest group of organic compounds are called alkanes. Okay, this is the very first thing I learned in organic chemistry in college. It's about alkanes. These are what are called hydrocarbons. So hydro meaning hydrogen, carbon meaning carbons, so substances of hydrogen and carbon, with each carbon bonded to 4 other atoms by single bonds. So alkanes only have single bonds. They are the simplest form. It says, notice that each molecule has the ane ending in its name. So methane, ethane, and propane. This denotes that it's an alkane. That's where that comes from. The prefix meth, eth, and prop are derived from the number of carbons present. So methane is something with 1 carbon, ethane is something with 2 carbons, and propane is something with 3 carbons. So if we're given just the name propane, we could say prop means 3 carbons, ane tells us that it's single bonded, and then we simply just fill in all the hydrogens around it to give each carbon its 4 bonds. So it's not too bad to do some basic organic. So just as a little practice, I want you guys to pause this for a minute, and you're going to try just naming these compounds. I gave you the list of the prefixes and how many carbon atoms it represents, and then I gave you some practice just analyzing some of the different models. So for number 1, we have the structural drawing, then we have a ball stick model diagram, we have a space filling model, and then number 4 is called a skeletal model. This one you have not seen before, so I want you guys to try it, see if you might be able to figure it out, and then you'll be able to check your work. So pause, and then we will discuss what the names are for each of these. Alright, so hopefully you've written down and tried these ones out. So let's look at them. Our first one, if we want to decide its name, we're going to look at its carbons. So there are 1, 2, 3, 4, 5, 6 carbons. Again, they're all single bonded. So 6 carbons means hex. This is the prefix. So because it's single bonding, it's bonded, it has that ane ending. So we would call number 1 hexane. Number 2, our ball stick diagram. Each one of these black ones, black dots, is our carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all single bonded to the hydrogens around them. So 9 carbons, single bonded, gives us nonane, N-O-N-A-N-E, nonane. Number 3, the space filling model. I think this is always the hardest one just because it's kind of harder to figure out how many carbons there are there. But there's 1 carbon here, 1 carbon up here behind this kind of hydrogen here, and 1 here. So that's 3 carbons. So that would give us propane because they're all single bonded. We don't really see all the hydrogens as easily represented here. We've got 1 hydrogen there, there. There's 1 kind of hiding back here. There's 1 here and 1 hiding back there. And then this last one should have 1 here, 1 here. And there's 1 on the other side that we can't see. So, but we assume that they're all filled in there. And then number 4, our skeletal model. This is the simplest form. And what it does is it takes this first one and it drops all the hydrogens and all the carbons, and it just gives us a very simple structure, kind of like this one too. At each of these points is a carbon atom. So just like in this, where at each of these points there was a carbon atom, we are going to say that here. So there's 1 there, 2, 3, 4, and 5. Okay, and it's single lines, so those are single bonds. So 5 would give us the prefix pent, and single bonds ane, so that would be called pentane for the 5th one. So that's how we can use the organic substances, the kind of basic prefixes to figure out some of their names and how they are written. So that's kind of the basics of some organic, and gives us some info and practice on looking at some of these structures.